Have you ever watched a movie where someone suffers an injury so bad they have to take a painkiller of some sort, and half an hour to 1 hour later, after popping those babies in, they're good as new? Are you tired of not knowing if antibiotics is right for you? Well, now you can. Have no fear of the neighborhood-friendly therapeutic drug monitoring, or TDM for short. And my name is Kendrick Lee, and this is my presentation. To start off, let's define what TDM is. TDM is a process that measures the adequate amount of medicine in your bloodstream to ensure it is safe and effective. Below is a chart of common medicines that need to be monitored. And as you can see here, the types of medicines is in this column, and the medicine names are in this column. Before we get into the mathematical aspects of TDM, let's talk about the important definitions that would be beneficial to our understanding of the math. Starting off with pharmacokinetics, this is the process in which a drug that is either orally and intravenously administered. And in this case, this would be the liberation phase. And from there, we can infer that the monetization would be through 4 different phases. This leads to the second phase. And that second phase is absorption. This is when the components of the drug enters the bloodstream either orally or intravenously. Next up, we have distribution. Distribution is the movement phase. This is when the drug is being transported throughout the body via blood transmission. And at this point in time, the drug should have taken effect, and it's going to be the strongest part. Next up is metabolism. This is when the drug is broken down, resulting in the drug's half-life to near completion. And this is at this point, this is when the drug should weaken. Finally, we have excretion. This is when the drug's effectiveness completely wears off, and from there, it is then excreted from the body through bodily functions known as excretia. Liberation, absorption, distribution, and metabolism are all part of the absorption phase, while metabolism and excretion are all part of the elimination phase. And it is important to note that these two will separate into 2 different equations. One would be an absorption equation, and the other one would be an elimination equation. Next up, we have important variables in order to write these equations. To start off, let's begin with defining the variables and their significance. There are 3 factors that contribute to the rate of absorption. The first is K of A. K of A represents how quickly the drug is processed throughout the body. For example, let's take a look below at these 2 graphs. We can see that most morphine takes approximately 1 hour to absorb and metabolize, as you can see here, 1 hour here. And for ibuprofen, it should take twice as long, totaling 2 hours. And ibuprofen here is 2 hours. Continuing on for our next variable, that variable is D. D represents the amount of medicine prescribed. For example, 2 tablets of morphine versus 1 tablet of morphine. Finally, for our absorption equation, we have B. B represents bioavailability. And in this case, this would be the drug absorbed divided by the total available drug. Continuing on to our elimination equation, K of E represents the elimination of the drug. And it also represents how long the body takes to eliminate the drug. Using the same example as before, morphine takes longer to be excreted than ibuprofen. Continuing on to our next variable, C represents the concentration of drug at any given time, and our final variable, V, represents volume. Applying differential equations. Now, as a non-STEM student, you may ask, how do we apply these differential equations? And in order to create models like these, when doctors use to find the concentration over time of a drug, we have to use differential equations. We use the absorption and elimination equations from the previous slide in order to create this final differential equation. And to define it, we can start off by separating both of these differential equations into subsections and define those 2. To start off, let's define the first one, d of A of G over d of T. This represents derivative of absorption over the derivative of time, and it is going to be equal to the amount of drug being absorbed over a given time. The next one, d of e over d of e times e of g over d of t. That represents the amount of drug being eliminated over a given time. So moving on to the next part, as we can see here, there's an inequality between the d of a of g over d of t and d of e of g over d of t. To define this one, when d of a over d of t is greater than d of e over d of t, absorption will take place, and vice versa. When d of a over d of t is less than d of e over d of t, elimination will take place. Medical professionals need calculus. With the absence of drug specialists in the pharmaceutical industry, identifying the concentration of medicine over a given period of time using calculus. Proper labeling and instruction of medication would be inaccessible for dosage. To summarize, calculus is necessary in order for medical specialists to be able to identify and recreate relationships between drug concentration in the body over a given period of time. And that's my presentation, and this is my works cited page. Thank you for listening.